Hello and welcome back to Math Class in Session. Next, the second derivative and concavity. On intervals where the second derivative is greater than 0, we can conclude the graph is concave up. In other words, it's shaped like a right side up soup bowl. And a point of interest is tangents happen to be below the graph. Here's a picture of something concave up. It's shaped like a right side up soup bowl, and it's just a point of interest here. This tangent is below the graph, as are all tangents. And the flip side of this coin, on intervals where the second derivative is less than 0, the graph is concave down. It's shaped like an upside down soup bowl. And tangents will be above the graph. Here's a picture of one. Concave down. And we can see that it's shaped like an upside down soup bowl, and the tangent we can see is above the graph. Points of inflection. Suppose that C is an x value where the double prime, f double prime of C, is equal to 0. If the concavity changes as x transits through C, which it probably will, then the point C, f of C, is a point of interest. It's called a point of inflection for this graph y equals f of x. Now I've got a picture of one here. This is a point of inflection because the concavity changes. To the left of the point of inflection, it's an upside down soup bowl, and to the right of the point of inflection, it's a right side up soup bowl. And so when the concavity changes, the name of the point is called a point of inflection. The second derivative test, well, it's a bit of a joke, really. I mean, it's a way to test a critical point to see if it's a max or a min from the first derivative prime line. So if you find a critical point, you can use the second derivative to determine if it's a max or a min in this way. If C is a critical number where f prime of C, not double prime, but f prime of C is 0, and the double prime is positive, then there exists a local minimum at C, f of C. So it's a way to tell, even though you've got the first derivative and you can just look at the prime line, if you can look at the second derivative too. If C is a critical number where f prime of C is 0, so we have a critical point, C, f of C, and the double prime is negative, well then we found a local maximum at that point. So this is using the second derivative to determine if critical points are maxes or mins, even though we can already do that with the first derivative. And I said it was a bit of a joke. Check with Mr. Y double prime. If Mr. Y double prime is feeling negative, here's Mr. Y double prime, he's feeling negative today, well, guess what you found? There's a max there. And if Mr. Y double prime is feeling positive, he's feeling positive, you can see he's happy, well, we must have found a minimum then. So that's the way to remember the second derivative test. Okay, let's do some analysis. Analyze for concavity using the second derivative. Solution, we got to draw a double prime line, which means you'll have to differentiate and then differentiate the derivative. So we got our double prime, set it equal to 0. So we'll set the second derivative equal to 0, and we have 6x equals negative 12 and x equals negative 2. It's a critical number, C, so we'll call it C equals negative 2, and we'll put it on our double prime line, negative 2, kind of like we did with a single prime line, and evaluate the intervals. On the left, sub in something large and negative to the double prime. That's why you label these things. Sub in something large and negative to the double prime, and we can see that that's going to be negative. And sub in something large and positive to the double prime, you can see that'll be positive. And that's enough for us to reach some conclusions. We can conclude that to the left of minus 2, it's concave down. Concave down for x less than negative 2. And concave up, because we see a plus sign, concave up when x is greater than negative 2. And there is a point of inflection. When x equals negative 2, the concavity is changing. And so to get the 1, we'll take negative 2 and substitute it in here, because this is where y values come from. They come from the original function. So we have a point of inflection. Carrying the conclusions forward to the graph. Here's the graph. According to the software, it looks like this, and there's our point of inflection, negative 2, 1. And you can see that to the left of minus 2, it's concave down, upside down soup bowl, and to the right of negative 2, it's concave up. Let's do it again. Let's do the whole thing again. Analyze for concavity, looks like a quartic. Solution, draw a double prime line, which means we have to differentiate a couple of times here. Priming, 4x cubed minus 12x squared minus 36x plus 30. Differentiating the derivative, 12x squared minus 24x minus 36, equaling it to 0. And I divided through by 12, because once it's equal to 0, you can divide through by a constant, not by a variable, but you can divide through by a constant. Factoring, because now it's a quadratic equation, solved by factoring, and x equals 3 or negative 1. Putting those numbers onto the double prime line, 3 and negative 1, well, there's negative 1, there's 3. Make sure you put negative 1 on the left of the 3. And we've got 3 intervals to evaluate. So we'll sub in something large and negative here. Because of the plus sign, we can go large and negative into the double prime, which makes this term, because it's large, this term becomes totally dominant. These two become insignificant. And a square is positive, so we know there's a plus sign there. In this interval, I can see the number 0 exists. So putting 0 in is very easy because this vanishes and this vanishes, and it's negative 36. And that's obviously negative. And something large and positive, well, this is, again, dominant, and so it's positive because it's a square. And this double prime line is enough for us to reach conclusions. We can say that to the left of minus 1, it's concave up, like a right side up soup bowl. And between minus 1 and 3, it's concave down. CD stands for concave down. So between minus 1 and 3, and this is how you say between minus 1 and 3 in math, between minus 1 and 3, it's concave down because of the minus sign, and elsewhere it's concave up. And CU stands for concave up, when x is less than minus 1 and when x is greater than 3. And we've got a couple of points of inflection because we can see the concavity changing as x transits through minus 1 and through 3. The concavity is changing, so we've got a couple of points of inflection. Negative 1, negative 43, and this negative 43 came from subbing negative 1 into that place where y values come from. This says y, and so this is where we'll get a y value. Similarly here, subbing in 3 into this, I suggest you do it, and getting negative 99. So we've got our points of inflection. We've got our intervals of concavity. Carrying all of our conclusions forward to the graph, we get the software saying the graph looks like this. A quartic opens up. There it is. There's the equation of it. We can see the concavity is concave down between minus 1 and 3. So between minus 1 and 3, it's an upside down soup bowl. And it's concave up when x is less than minus 1. So there's x being minus 1. Now here's the right side up soup bowl. We can see it's concave up. And similarly to the right of 3. X greater than 3, it's also concave up. Here's our points of inflection, which I carried forward, and we can see them here. Negative 1, negative 43, point of inflection, from concave up to concave down. And 3, negative 99, from concave down to concave up. Now you can check these because I made the y's count by 50s. So negative 50, negative 100 is right about here, so this is negative 99. This is negative 50, so this is negative 43. And one last time, let's do it again. Okay, this isn't a cubic, this isn't a quartic, this is a bit of a challenge. Analyze for concavity. Solution, draw a double prime line. That's how you analyze for concavity. To do that, we have to differentiate it twice. Okay. Well, I like to write it this way. So I haven't differentiated. I just rewrote the function with a negative exponent because now it becomes easier to differentiate, in my view. So it will be negative 1 times all of this to the negative 2 times 2x. There's your first derivative. Now we have to differentiate the derivative, and that means it's a product of functions. So it will have to be first thing prime times the second thing, etc. First thing primed is negative 2 times the second thing, well, the second function of x, which is x squared plus 3 to the negative 2, plus the derivative of the second function of x times the first function of x. So it will be, let's see here, negative 2 times all of this to the negative 3 times the derivative in here, which is 2x, times the first thing, which is negative 2x. So there it is, raw. We need to simplify. So we have work to do on this. Well, let's see. This term here is all multiplied. So it's a negative times a negative, which is a positive, and 2 times 2 times 2 is 8, and that x times that x makes x squared. So tidied up, it looks a little more tidy. Now comes, we have to set it equal to 0 and solve it. That's how we're going to draw a double prime line. So what we do is common factor. And when you common factor complex expressions like this, look for factors that are common and take the lowest, the least exponent. Common factor out the 1 to the least exponent. Now negative 3 is less than negative 2. So x squared plus 3 is common to both. So x squared plus 3 to the negative 3 will come out common. Here it is coming out. X squared plus 3 to the negative 3. And I took negative 2 out as well because 8 is a multiple of 2. Checking our work. And what's in the square brackets is the residue. It's the result of dividing x squared plus 3 to the minus 3 out of each of these terms. Now when you take it out of the first one here, you're left with x squared plus 3 to the positive 1. Now the minus 2 is out here. Now you can be a skeptic and say, I don't think so. Well, let's find out. If you multiplied this back in, we would have to add exponents, and negative 3 plus 1 is negative 2, so this is right. But be skeptical and check your work. Now when you take negative 2 out of plus 8, you're going to get negative 4, and still the x squared, but this has been common factored out. So maybe, if necessary, pause the video and dwell on this step. It's a pretty important step. Now, to continue, we've got x squared minus 4x squared, which is minus 3x squared, which is a little awkward. So I put this negative sign back in. So x squared minus 4x squared is negative 3x squared times the negative makes it positive 3x squared, like this. And that plus 3, of course, will have to be negative 3 now, or subtract 3. Now it's starting to look very tidy. And out of this factor can come another 3. So we'll common factor out of 3 and make the 2 into a 6. Now it's really starting to look good. So all we need to do is put this factor on the bottom because it's got a negative exponent, and we have it. Now I'll dispense with all the work and just put the result, but I suggest that you differentiate and be able to differentiate that for yourself. So here's the result of our differentiating. We're going to set it equal to 0 and put the critical numbers on the double prime line. There's the double prime line. Now we can see that x can be plus or minus 1 from this numerator factor because the denominator will always be positive. Something squared plus 3 is positive because squares are positive. And just look at the numerator and set it equal to 0, which means that x squared minus 1 has to equal 0, so x is plus or minus 1. Put them on the double prime line and start evaluating the intervals. Something large and negative. Well, the denominator is always going to be positive, and if it's large and negative, the x squared becomes dominant, and that's positive. A number between minus 1 and 1 is the number 0. Placing that in here, we have negative 6 over something positive, and that will be negative because it's negative 6 over a positive. And something large and positive, placing it in here, again, the square will be positive over a positive, and so we have an interval of concavity up, a plus sign. This is plenty of information to reach conclusions. Wherever we see a negative sign, it's concave down. So concave down between the ones, between negative 1, less than x, less than 1, and all the other places it's concave up. Concave up for x greater than 1, and concave up for x less than negative 1. And we've got a couple of points of inflection here. Points of inflection. POI at -1. And where does the y value come from? Placing -1 right into where y values come from. -1 squared is 1 plus 3 is 4, and 1/4 is 0.25. So -1, 0.25, and +1, 0.25. Because again, if you sub in 1, you got +1 squared, which is 1 plus 3 is 4, and 1/4 is this 0.25. Carrying our conclusions forward to the graph, according to the software, it looks like this. And we can see our point of inflection here, -1, 0.25, -1, 0.25, and +1, 0.25 are points of inflection. Our intervals of concavity, it's concave up to this point, and then it's concave down, it's an upside down soup bowl, and then it's concave up. So this is information from our second derivative displayed on a graph.